Hello all. Welcome to our online version of Math 1240 Pre-Calculus. And today we're going to look at section 4.1 of the Stewart book. And this is on exponential functions. And we're going to start by looking at the exponential function base 2. So this is the exponential function base 2. And that function looks like this. I'm going to call it g of x, and it's equal to 2 to the x power. So the 2 here represents our base. You'll remember from college algebra that there are some properties of exponentials, and I'm going to frame those properties in terms of exponentials base 2. If I look at 2 to the 0 power, what do we know? We know that this is equal to 1. If I look at 2 to the x power times 2 to the y power, this is equal to 2 to the x plus y power. And the other property is that 2 raised to the x power, all raised to the y power, is equal to what? 2 to the x times y power. All right, so these are all properties of exponentials base 2. And we also have this. We have the 2 to the minus x power is equal to 1 over 2 to the x power. Okay. How might I see that? Well, you'll remember that if I have 2 to the minus x and I multiply it by 2 to the x, this is equal to, what is this equal to? This is equal to 2 to the minus x plus x power. That's using this property over here. And this is equal to 2 to the 0 power. And we know from the first property that we listed that 2 to the 0 power is equal to 1. So I have that 2 to the minus x is equal to, dividing both sides by 2 to the x, is equal to 1 over 2 to the x power. Okay, so these are some of the main properties of exponentials, and we can actually translate those into terms of our function g of x equal 2 to the x. So if I look at g of x plus y, this is equal to, well, what is this? This is just 2 to the x plus y power, which we know from property 2 up here on exponentials. This is equal to 2 to the x times 2 to the y, and that's equal to, well, 2 to the x is equal to g of x. And 2 to the y, well, 2 to the y is just going to be g of y. So isn't this interesting? We have a function, g, that has the property that g of x plus y is equal to g of x times g of y. So this is a property of the exponential function. And furthermore, g of 0, well, we know that's 2 to the 0, and 2 to the 0 is equal to 1. Right? Let's take a look at a graph of the exponential function. So we want to look at the graph of g of x. And, when you graph a function, one of the things you really have to know is what is the domain of the function. So what is the domain of g of x? Well, the domain is the set of real numbers such that g of x can be defined. And g of x we know is equal to 2 to the x power. And 2 to the x power is defined for all real numbers. So this is defined for all real numbers. And so what we have, so this implies that the domain of g of x is equal to the set of all real numbers, which sometimes people denote by a capital R, or in our case, this is probably a little bit better. We're going to use interval notation, and I'll denote this by the open interval from minus infinity to plus infinity. Okay, so that's the domain. That's the domain of our exponential function base 2, g of x is equal to 2 to the x power. Well, let's plot some points. That'll get us at least an idea as to what this exponential function, its graph might look like. So here I'm going to do this. All right, so this is my y-axis, and here's my x-axis. And let's go over here. We know that g of 0, this is, and I'm going to write this here again. G of x is equal to 2 to the x. So g of 0 is equal to not 0, no, it's equal to 1. That means that the point with coordinates 0, 1 lies on the graph of my function. And then we're going to do g of 1. And g of 1 is just 2 to the 1, which is 2. I'll write a few of these down over here, and then we'll plot them. So g of 2 is equal to 2 to the 2, which is equal to 4. G of 3 is equal to 2 to the third power, which is equal to, well, it's going to be 4 times 2, and that's going to give me 8. G of 4 is equal to 2 to the fourth power, and that's 2 times 8, which is 16. And I don't think I'm gonna be able to plot any more points. So here we are. We're at, here's 1, here's 2, here's 3, here's 4. 1, 2, 3, 4. At 1, we're at 2. At 2, we're at 4. At 3, we're at 8, which is here. And then at 4, we're up here to 16. I think that's 16. I'll bet it's 1 up. Let's see, 1, 2, 3, 4. Yep. Oops. Gonna have to extend this a little bit, and we'll plot it all the way up here. There it is. So we have 4, 16. And then here this is 3, 8. Here this is 2, 4. Here we're at 1, 2. Our function looks a little like this. Like that. And now let's go over here. Minus 1. There's minus 1. And g of minus 1 is equal to 2 to the minus 1 power, which is equal to 1/2. So we're going to have a point here. And yeah, that's the point, minus 1, 1/2. And then g of negative 2 is equal to 2 to the negative 2 power, which is equal to 1/4. And so that would be right about here, like so. And this curve is just going to get closer and closer to the x-axis without ever touching it. okay? And I can't draw that, of course, but what we find is the following. So from the graph, what can you tell me about the range of g of x? Well, remember, the range of a function is the set of values y which are covered by the graph. And those values of y that are covered by the graph are the values from 0 to plus infinity. Okay, so they're all the positive values, positive real numbers. Notice that the x-axis is an asymptote. It's an asymptote of g of x. All right. Certainly as x goes to minus infinity. So as x approaches minus infinity, g of x approaches 0. Okay? And another way of writing that, you might have seen this before when you studied rational functions. This is saying that the limit as x goes to minus infinity of g of x is equal to 0. Sometimes you might see this written, the limit as x goes to minus infinity of 2 to the x power, this is equal to 0, all right? And then we can write down another limit. So from our graph, it's pretty noticeable that as x increases, the values of our exponential function increase very, very rapidly. So we can say that the limit as x goes to infinity of g of x, this is equal to plus infinity. Okay. Our function g of x is an increasing function. What does that mean? So increasing function, well, you'll remember that if I have two numbers x and y, and x is strictly less than y, then if g is increasing, that implies that g of x is strictly less than g of y. So if I have this strict inequality, x is strictly less than y, then I know that g of x is going to be strictly less than g of y. This is an increasing function. Well, sadly, this exponential function is used to model the number of coronavirus cases occurring in the state. And what we find is that with the coronavirus, the doubling time in New Mexico is approximately 3 days. Okay, so I'm going to call one time unit is equal to 3 days. Okay, so here we have this is time, or time units down here. And over here, the number of detected cases. And suppose at day 0, when they first started testing, we had only one case being detected. And on the first time unit, there are 2. And on the second time unit, there were 4, because this function, let's call it c of t, this is equal to 2 to the t power, okay, where t is a time unit, which means that it's equal to 3 days. Okay, here's 4, this is 3, so we have 8. Where does that put us here? And then at day 4, we're way up here. Let's see if I can, oops, keep on doing that in the wrong direction. We're here, okay? So this is what the number of cases as a function of time units looks like for the state of New Mexico. And this is exponential growth. Suppose I wanted to translate this. Suppose I didn't like this time units axis down here. I want this in days. So what do we know? We know 1 time unit is equal to 3 days. That means that 1 day is equal to 1/3 of a time unit. All right. So if I want to look at this, so if I have g of x, where x is measured in days, this is equal to, well, this is equal to c of t divided by 3, because 1 day is equal to 1/3 of a time unit. So x days is equal to t time units divided by 3. Actually, I'm going to make that x, right? And this is equal to 2 to the x divided by 3. So this is the model of coronavirus growth in New Mexico as a function of days. So it looks like g of x is equal to 2 to the x divided by 3, which I could also write this way. So you'll remember one of our properties that we had listed of exponentials is that 2 to the x times y power is equal to 2 to the x times 2 to the y. So I can write this as 2 to the 1/3 times x, and that's equal to 2 to the 1/3 raised to the x power, and this is equal to the cube root of 2 all raised to the x power. Okay. So now I would like to give you a problem to work on. And the problem is I would like you to graph the following. I'd like you to graph, let's say 2 to the x power plus 1. So let's call it y equal to 2 to the x power plus 1. That's the equation I want you to graph. Another one is y is equal to 2 to the minus x minus 1 power. So work on those two problems, and then make sure you look at the suggested problems that are associated with section 4.1 in the modified syllabus. Okay, take a look at that for me, please, and we'll talk again soon.